So I think we can start now. I hope you all are ready. So I welcome you all to the first tutorial of this course, Introductory Organic Chemistry 1 by NPTEL. I'm Deepika, your PMRF teaching assistant. I'm doing my PhD in chemistry from IIT Bombay. And the course instructors of this course are Professor Harinath Chakrapani and Professor Neeraja Dashaputri from IISER Pune. I hope you all know that Professor Neeraja has already conducted 3 classes on this course in the first week, which were on the topics structure of atoms and molecules, followed by molecular orbital theorem. So, how many of you have watched the videos by ma'am? Have you watched or not? Feel free to interact in this class. Okay, some of you have watched. And I would like to tell one more thing to you. Please feel free to ask any questions or queries that arise during the class. Uh, I will try my best to solve all the questions and queries arised by you during the class. And any doubts regarding the course, you can feel free to ask me. Okay. So let us start the tutorial of this week. So the first question we have today is the ion isoelectronic with carbon monoxide is. There are 4 options given here: O2 minus, N2 plus, Cn minus, and O2 plus. So out of these 4 options, which ion will be isoelectronic with carbon monoxide? So I would like to ask you all to try to solve this question. So we will definitely solve the question together. So first of all, what we will have to do to find the isoelectronic ion of carbon monoxide? We will have to calculate the number of electrons present in carbon monoxide, right? And for that, molecular orbital theory will help us. See, here I have included this molecular orbital diagram of N2 plus, from where you can know the number of electrons present in the N2 plus molecule. Of course, it is a cationic species, and if you count the number of electrons in the N2 plus molecule, you will find this sigma 1 is possessing of 2 electrons, sigma star antibonding is possessing 2 electrons, and followed by 4 electrons in pi 2px and pi 2py orbitals, and then sigma 2pz will have 1 electron. So total number of electrons present in this N2 plus species is 9. Okay, till here does anybody have any query? I hope you all are familiar with molecular orbital theory, right? Okay, so we know that in molecular orbital theory, according to MOT, atoms undergo combination to form bonding and anti-bonding orbitals, right? So here we can see that bonding orbitals possessing electrons and anti-bonding orbitals are possessing electrons, and like that N2 plus is having total 9 number of electrons. Similarly, in options we have O2 minus and O2 plus also. For that I have shown oxygen molecules molecular orbital diagram, and here you can see it. If you count, it possesses 16 electrons in the molecule. So for O2 plus, it will have 1 electron less, and for O2 minus it will have 1 electron more, which will like for example, for O2 plus, 1 electron from the pi star orbital will leave, and for O2 minus, 1 new electron will enter in the either pi 2px star or or pi 2py star. So thus in O2 plus we will have number of electrons 15, and in O2 minus which will have extra 1 electron, will have 17 electrons. And in the parent, in the question, we are mentioned that isoelectronic with carbon monoxide. So if you count in the carbon monoxide, you have 10 number of electrons in the molecule. And cyanide molecule, cyanide species Cn minus undergoes molecular or orbital combination to undergo uh, a molecular orbital diagram of such type, which will have total number of electrons if you count 2, 4, 6, 8 and 10. So now we know the number of electrons present in the species given in the options. In O2 minus we found 17, N2 plus we found definitely not equal to 10, because in carbon monoxide we have 10 electrons and in cyanide we found 10 electrons. O2 plus also we had 1 electron less than oxygen molecule, which was 15. So thus we found that the ion which is isoelectronic with carbon monoxide will be option C, cyanide. Is it clear? Okay. Does anybody have any question? Please don't hesitate. I will definitely love it to solve your queries. Okay, so if it is clear to you all, let us move to the next question. Okay. So next question we have, which of the following set of quantum numbers belong to highest energy? So we know there are four kinds of quantum numbers uh, for one electron. So you have to find out which set of these four quantum numbers belong to the highest energy. So does anybody know, to calculate the highest energy, what do we see in terms of quantum numbers? What do we see? Does anybody have any idea? Okay. Okay. Any other answer? Okay. Very nice. What is your name? Okay. Great. So any other answer or any comment on her answer? Yes. Okay. So very good, Dr. Payal. So yes, we will have to see n plus L value, principal quantum number, plus azimuthal quantum number. So addition we will have to see for which set it is highest. But suppose this addition value is same for two sets, then we will have to move to see the higher principal quantum number. Yes, very good. So here, as Dr. Payal said, that we will see the addition of n plus L. Uh, you don't get confused that do we have to see only principal quantum number first, or do we have to see the combination? Always remember, we will have to see the combination first. Okay, after that only we will move. If the combination is same, like the addition is same, then only, like for example C, we have B and C. Okay, in C we will have addition 3, and B we will have addition 3. So if such case arises, then only move to principal quantum number. So yes, here we have the correct answer is D. Do not get confused with option number A, where principal quantum number is 4, because here the addition is 4, but here in D the addition is 5. So this was the question number 2, and let us move to question number 3. The orbital diagram in which above principle is violated is. So here four sets of electronic configurations are shown. In the first lecture by Professor Neeraja, she taught you these principles, how electrons are arranged in orbitals, shells and subshells. So based on that, you have to figure out which set of these four is violating our above principle? The above principle dictates the manner in which electrons are filled in the atomic orbitals of an atom in its ground state. So electrons are filled in the order of increasing order of the orbital energy level. Okay. So, okay. Answer is B. Okay. Any other answer? So, according to our above principle, atomic orbitals with the lowest energy levels will be occupied first, and then only we will move to occupy the higher energy levels. Okay. So, thus, in these four, we will have to say that 2s will be filled first. After that only we will move to p orbitals. So like she said, answer will be D. You cannot fill the p orbitals before fully filling the 2s orbital. Okay. Uh, Sorry, is this Payal? Did you say B? Yes, yes. Because see, yes, yes. Before filling the 2s, the electron is moving to 2px. So answer is B. Okay. So, in for question number 3, the answer is B. Is this question clear to everybody, or does anyone have any query? This is easy question, I hope. Is it clear? Okay. Please feel free to ask any query, okay? No one is here to judge. We all are here to learn. So, with this, let us move to question number 4. Isotopes of an element have. I have given you 4 options. Do they have different chemical and physical properties? Do isotopes have different chemical and physical properties, or their chemical and physical properties are same? So can anybody tell me what are isotopes briefly? Can anybody recall the definition of isotopes? Okay, very good. Yes. So if two uh, atoms have same atomic number but different mass number, they will call they will be called isotopes. Like for example, hydrogen and deuterium. And you have chlorine 35 and chlorine 37 also. They are also isotopes. So isotopes will have different chemical physical properties or similar chemical physical properties, or they will differ in either chemical or physical properties. Yes. Okay. What is your name? Okay. So the answer is isotopes will have similar chemical properties, but they will be different physical properties. Like for example, melting point, boiling point, etc. But chemically, isotopes will behave exactly similar. Like for example, in chemical reactions we see, in organic chemistry we see, uh, for suppose hydrogen, 1,5 hydrogen shift reactions we study. So, in case of hydrogen and deuterium, for example, if hydrogen shift is occurring, similarly deuterium shift will also occur in the same manner because they will have similar chemical properties. Is it clear to everyone? I hope no one has any doubt on this. Okay. So let's move to the next question. This is a very easy question. Number of pi bonds in naphthalene molecule is 6 or 3, 4 or 5. For that you all will have to know the structure of naphthalene. So how many of you know the structure of naphthalene? Okay. And if we join 3? Okay. Very nice. Yes. Okay. So the structure of naphthalene is two benzene rings fused, and we get 5 pi bonds present in this molecule. So the answer will be option 5. Okay. And let us move to question number 6. Find the paramagnetic species: cyanide, nitrous, carbon monoxide, and O2 minus. So among these four, which of these species is paramagnetic? To find out the paramagnetic species, how do we start answering the question? How do we approach this problem? Anyone? Which theory will help us? Yes, very good. What is your name? Okay. Uh, like you said, we will be directed by molecular orbital theory. Bonding and anti-bonding molecular orbitals, number of electrons will help us. So first of all, to answer this question, we will have to draw the molecular orbital diagrams of these four species. And then we will place the electrons one by one in the bonding and anti-bonding molecular orbitals, which are formed by atomic orbital combinations, and then we will have to see which of these species contain unpaired electron. Whichever species contain unpaired electron in the molecular orbital diagrams of these species will be paramagnetic. And if the species contain only paired electrons in the molecular orbital diagrams, they will be called diamagnetic. So for that we will need the molecular orbital diagrams. Like here you can see, this is the molecular orbital diagram of N2 plus. NO plus. This is O2 plus, carbon monoxide and cyanide. The option were given: cyanide, NO plus, carbon monoxide and O2 minus. Cyanide, carbon monoxide, NO plus. So has anyone found out the answer? We don't require N2 plus here, since the options given are only cyanide, nitrous, carbon monoxide and O2 minus. Has anyone found out the answer yet? So by looking at the molecular orbital diagrams, we see that O2 minus has one unpaired electron. Like we calculated in question number 1 already, it has 17 electrons in its molecular orbital diagram. of which one electron is unpaired. So, out of these four species, O2 minus will be the paramagnetic one. Okay, is it clear? I hope it is clear to everyone. Does anybody have any doubt? Okay, so let us move to the next question. The oxygen molecule is paramagnetic. It can be explained by which of the following theories? I hope this is a very simple question. Since we have already calculated or found out the paramagnetic species in the earlier question, question number 6. So you can easily find out that which of these following theory can dictate that oxygen molecule is paramagnetic. What will be the answer? Anyone? Okay, very nice. See, resonance will give us the number of resonating structures in a molecule, which will account for its stability. Similarly, hybridization theory will give us shape and geometry of molecules. So out of these four options, molecular orbital theory will tell us the paramagneticity and diamagneticity of of molecules. PVT also, like valence bond theory, will give us the geometry and orientation on and shape of the molecules, but not it will not directly tell us that the oxygen molecule is paramagnetic or diamagnetic. So for that we will need the help of molecular orbital theory. So the option is, like he said, option D. Next question is also one of the simplest questions of this series. Combination of two atomic orbitals results in the formation of two molecular orbitals, namely one bonding and one non-bonding orbital, or two bonding orbitals, two non-bonding orbitals, or two bonding and non-bonding orbitals. So, will anyone want to try the answer? This is one of the basis of molecular orbital theory. Two atomic orbitals will combine, and they will have combination in a uh, constructive way to form one bonding molecular orbital, which will have lower energy, and also they will form one non-bonding one anti-bonding non-bonding orbital, which will have higher energy. So this molecular orbital theory was given in 1932 by Hunt and Mulligan. According to this theory, the combination of two atomic orbitals can give us two molecular orbitals, namely one bonding and one non-bonding orbital. So the answer is A. I hope it is clear. Okay. Let us move. Yes. Okay. So um, yes, actually, yes. Yes, and usually in molecules we find bonding and anti-bonding, and in non-bonding orbitals we place the lone pair of electrons which do not participate in the bonding. Okay, actually, I will definitely clear your doubt. I will like study further, and then I will try to solve your query in on this question in the next session. Is this okay? Because yes, according to me also, it should be one bonding and one anti-bonding orbital. But since in the four options provided, we do not have any anti-bonding orbital placed in the options, that is why I think the answer is mentioned as option A. But yes, I will definitely try to clear your doubt on the next session. Maybe the question is wrong, framed in a wrong way, so I will clear. Okay. But if the option are only these four options are given, then we will have to answer it as one bonding and one non-bonding orbital. Okay, so with this, let us move to the next question, question number 9. What is the bond order of oxygen molecule? Can anyone tell me the formula of bond order? How do we find it? Like in oxygen, we all know how many bonds are present, but how do we theoretically calculate it? What is the formula? Okay, okay. Any more answer or any comments on his answer? Okay, very good. Both answers are correct. So it will be number of electrons placed in the bonding molecular orbital minus number of electrons placed in the antibonding molecular orbital divided by 2. So this is the molecular orbital diagram of oxygen molecule. If you count, we can see that in sigma 2s we have 2 electrons, in sigma star 2s we have 2 electrons placed, and similarly if we go further in the higher energy molecular orbitals, we will find that the oxygen molecule contain 10 electrons placed in sigma bonding orbitals, like you see here, these two, these two, and followed by these two. So like this you will have 10 electrons in the bonding molecular orbital and 6 electrons in the anti-bonding molecular orbital. Thus if you calculate half bracket Nb minus Na, you will get that the bond order in oxygen is 2. Thus oxygen molecule will possess 2 bonds between the oxygen atoms. Can anyone recall the relation between bond order and bond length? Okay, very nice. Yes, higher the bond order, lesser will be the bond length. Like for example, you see ethene and ethine. In ethene, we have carbon-carbon double bond, and in ethine, we have carbon-carbon triple bond. So, bond order is 3 in ethine. So, the bond length is inversely proportional. So, it will be less for carbon-carbon triple bond than carbon-carbon double bond. So, I hope this answer is clear to everyone how we calculated the bond order. Let us move to the next question. The next question we have the orbitals that are resulted from sp hybridization have dash percent s character and dash percent p character. You are given 4 options A, B, C, D. You have to find out the one sp hybridized orbital will have how much percentage of s character and how much percentage of p character. I hope this is a very simple question. Can anyone will anyone try the answer? Yes, yes, very good. For sp hybridization, it will be 50-50. What if it is sp3? What will be the ratio, or what will be the percentage division for sp3? Okay, okay. So theoretically, we all know that in sp hybridization, one s and one p orbital undergo hybridization. One sp orbital will have 50%, like you said, and 50% p character. And sp hybridization, I hope you know, possess linear geometry, and it is also called diagonal hybridization. So the answer will be B, 50-50. So we have like that covered 10 questions. Now we are also left with a few more questions. But till now, do you have any queries or comments? Do you have any comments or queries on whatever questions we have already discussed? Okay. So I hope we can move to the next questions. We have question number 11. What type of hybridization does a BCl3 molecule undergo? Boron trichloride molecules hybridization, you have been asked, and you are given three options. Is it sp hybridized? Is it sp2? Is it sp3, or is it sp3d? Okay. Any other answers? So yes, like she said, boron trichloride undergo sp2 hybridization. One s orbital and two p orbitals undergo mixing or combination and form three equivalent sp2 hybrid orbitals in boron trichloride. And the geometry of BCl3 will be like trigonal planar shape, where boron will be in the center and the chlorine atoms will be placed in three corners in the planar shape. Is I hope you all are being able to imagine the uh, trigonal planar shape of BCl3 molecule, right? Or is there any problem in that? So we have found out that it possesses sp2 hybridization. Since it doesn't, the central atom boron doesn't have any lone pair electron, so it will not possess any scenery of lone pair bond pair or bond pair repulsion or interaction. So we will have one trigonal planar geometry and planar shape of this molecule. So like this, the chlorine atoms will be oriented in such a way, and the does anyone know the bond angle that BCl bonds will have? Yes, yes. And what is the bond angle in case of tetrahedrals? Yes, it is 108 degrees and a few minutes. Yes, you can tell it as 109 degrees. So in case of sp2 hybridization, we have 120 degrees between the boron and chlorine bonds. So like this, BCl3 molecule will have sp2 hybridization, and trigonal planar shape. I hope this answer is clear to everyone. Let's move to the next question. Compound having planar symmetry among the four options provided: H2SO4, H2O, HNO3, and CCl4. Sulfuric acid, water molecule, nitric acid, and carbon tetrachloride. Among these four molecules, which molecule will have a planar symmetry? To find out the symmetry, we will be helped by the hybridization of the molecules, right? So for that, we will have to first find out what is the hybridization possessed by the molecules given. If you want to find out the hybridization, it will be given by this formula. Of course, you can take help from any other formulas also, where many other ways of calculating hybridization is used. As the standard method, we can use this formula: half inside bracket V plus H minus C plus A, where V gives us number of valence electrons in the central atom, H is number of surrounding monovalent atoms, C is cationic charge, and A is anionic charge. So if you have cationic charge, you will have to subtract the charge in the formula, and if you have anionic charge in the species, you will have add the charge in the formula. So first of all, you will have to look at the central atom of the molecule. In case of H2SO4, the central atom you have to identify as sulfur. Like Professor Neeraja ma'am has said in her class, that the central atom, you have to choose the atom which forms the maximum number of bonds. So whatever atom in the molecule forms the maximum number of bonds, that will be your central atom. Like for example, in nitric acid, it will be nitrogen. So here also you have to choose sulfur as your central atom, and then you will have to find out the hybridization of H2SO4. So now let us try to find out the hybridization of H2SO4. Has anyone found out yet the hybridization of sulfuric? Okay, you have found out the answer already. So what will be the hybridization of sulfuric acid? Is it sp2? Is it sp3? Is it sp3d? Yes. So remember one thing, for H2SO4, whenever you calculate, you have to consider the anion, okay? The SO4 minus anion, because we are considering the hybridization of sulfur, so it is in the anionic form. So for the anion, if you calculate the hybridization state of sulfur using this formula, you will find that sulfur is having sp3 hybridization in this molecule. And sp3 hybridization corresponds to which geometry? Anyone? Like in case of boron trichloride, we found that sp2 hybridization is corresponding to trigonal planar geometry. Similarly, sp3 hybridization corresponds to which geometry? Is anybody wanting to try? Okay, sp3 corresponds to tetrahedral geometry. Of course, the shape is dictated by the presence of number of lone pair electrons in the central atom, but since it doesn't have any number of lone pair electrons now, so its shape and geometry will be tetrahedral. Similarly, if you try to calculate the hybridization state of oxygen in water molecule, what is the hybridization here? Has anybody found out? Yes, water molecule is also possessing an sp3 hybridization state, but is the shape of water molecule tetrahedral or is it different? Yes, yes. Yes, yes, very good. Yes, like she said, although oxygen atom in water molecule possessing sp3 hybridization and its geometry is tetrahedral, but due to the presence of lone pair of electrons in the oxygen molecules, like you can see, if you draw the Lewis dot structure of water molecule now, you will find two electron pairs in the oxygen atom. Okay, so due to the repulsion between lone pair bond pair and lone pair electrons, the actual shape of the water molecule will distort from its ideal tetrahedral shape, and due to which the shape of the molecule will be bent or V-shaped. Is it clear? I hope the geometry of water and shape of water is clear. So next option we had was nitric acid. Like Dr. Payal has already told us all that the answer is option like nitric acid, option C. But let us find out the hybridization of the remaining molecules, nitric acid and CCl4. As we calculated hybridization states of sulfur and oxygen in these molecules, in the similar way, we will find that hybridization of nitrogen in nitric acid molecule is sp2, and which will dictate the geometry of this molecule to be trigonal planar. In CCl4, the hybridization and geometry will be similar to methane molecule. So it also like in this molecule also carbon is possessing sp3 hybridization and it will have tetrahedral geometry. Thus, out of these four options given in this question, option C, nitric acid will have a planar symmetry. This will have sp2 hybridization possessing a trigonal planar geometry or shape. I hope this answer is clear to everyone. So, in the next question, we have in benzene, all the 6 carbon-carbon bonds have the same length because of which of the following reason will be correct? Is it tautomerism? Is it due to sp2 hybridization of the carbon atoms? Is it isomerism or is it inductive effect in the atoms of benzene molecule? Which theory will dictate the same bond length in the all 6 carbon-carbon bonds? What will be the answer? Anyone? Yes, very good. The answer is sp2 hybridization. In case of benzene molecule, we do not see any tautomerism. Like in case of ketoenol tautomerism, we see carbon-carbon double bond, and one carbon can have hydroxide functional group, and then the carbonyl, suppose aldehyde. So in such case, we find tautomerism present, but in case of benzene, we do not see any tautomerism. Similarly, isomerism and inductive effect, we although inductive effect we can see partly in benzene molecule, but the six similar length similar length having carbon carbon bonds are found in benzene, not due to isomerism or inductive effect. It is due to sp2 hybridization present in benzene molecule. Like here you can see how the p orbitals which have not participated in the sp2 hybridization possess lateral overlap to give you such pi clouds in this molecular plane. Each sp2 hybridized carbon in the ring has an unhybridized p orbital which will be perpendicular to the ring, and it overlaps around the ring. The two lobes of the unhybridized p orbital you can see above and below the molecular plane, and these two lobes undergo lateral overlap to give us pi interaction. Pi interaction. So 6 pi electrons are delocalized over these 6 carbon atoms due, which is governed by this pi interaction present between the unhybridized p orbitals. So thus we have the answer as sp2 hybridization present in benzene will dictate the same length of carbon-carbon bonds. Is this answer clear to everyone? Or does anybody have any doubt? Okay, I hope it is clear. Let's move to the next question. The main axis of a diatomic molecule is Z. Molecular orbital px and py overlap to form which of the following orbital? Option A, pi molecular orbital. Option B, sigma. Option C, gamma molecular orbital. Or D, no bond will be formed. Let us try to visualize. So you have been asked that the bonding orbital lies along this z-axis. And you have x and y axis perpendicular to this z-axis, which contains the bonding orbital. So the question is, molecular orbital px and py will overlap to form which of the following orbitals? Whatever orbitals of the atoms combining are along y and x axis will combine to which type of interaction? Will it give sigma, or will it, like for example, we have the y-axis of the two atoms which are undergoing combination to give us bonding here. Okay, these are the two bonding orbitals of the, suppose, or atom A and atom B. This is the Z axis, and here it is Y axis. So the interaction present along the Y and Y directions, is it bonding or is it anti-bonding? What kind of interaction will it give? Is it sigma bonding or is it kind of pi interaction? What kind of overlap it will undergo? Anyone? Yes? Which option did you say? Okay, very good. So we all know that to form sigma bonding molecular orbital, we will have direct interaction or overlap. But if you have lateral overlap, you will be remain with pi molecular orbital, because they will have pi interaction in between the atomic orbitals of the two atoms undergoing molecular orbital combination. So the option is yes, it will be A. The molecular orbital px and py will overlap to form a pi molecular orbital. The next question, question number 15. What is the formal charge of silicon in silica, SiO2? You have been given four options: 0, -1, +2 or -2. Here the central atom is silicon. You need to find out what is the formal charge of silicon in this silica molecule. Does anybody know the formal charge calculation formula? Ma'am had already taught you. I remember, as I remember, she has taught you the formal charge calculation formula. Can anybody recall how we calculate formal charge? So the formal charge calculation is given here. It is number of valence electrons present in the central atom of the molecule minus number of lone pair electrons, not lone pairs, okay? Lone electrons present in the central atom minus number of bonds formed by the central atom. So as you can see, in case of silicon in silica, of course in this formula you can see that you have been given as minus b by 2. If you are considering bond pair electrons, then you have to divide it by 2. But if you are considering number of bonds formed by the central atom, then you do not have to divide it. Like, I hope it is clear. If you are considering the bond pair electrons, then you don't have to divide it by 2. But if you are considering the individual electrons, like in case of lone pair electrons, we consider individual electrons. If you are considering individual bonding electrons, then you have to divide the number of bonding electrons by 2. So the formula goes like number of valence electrons in the central atom minus number of non-bonding valence electrons minus total number of electrons shared in bonds divided by 2. So like that, if you try to calculate the formal charge of silicon in silica, we all know what is the valence shell electron number in silicon. Anyone? Number of valence shell electrons in silicon? Okay, it comes from the same group as carbon. So the number of valence electron in silicon will be 4. Okay, so if you calculate the formal charge, it will be 4 minus, since it doesn't have any lone pair in the silica, because all the 4 electrons, valence electrons, have participated in formation of bond. So you are left with no lone pair electron. So it will be 4 minus 0 minus number of bonds formed by the central atom. You have to count all the sigma and pi bonds also. Okay. So as the formula goes, 4 minus 0 minus 4, as it is forming 4 bonds, the answer will be 0. Is it clear? I hope it is clear to everyone how we calculated the formal charge of silicon in silica molecule. Thus, we are left with the answer as 0. So the option will be option A. So we have till now covered 15 questions on the topics taught in week 1 by Professor Neeraja ma'am on structure of atoms and molecules and molecular orbital theory. Does anybody have any query or any comment on the questions discussed? Or do you have any comment on the type of questions where the questions too easy, where the questions hard? What kind of questions were included in the tutorial? Any comments from the students? Okay. Yes, yes, good question. Actually, yes, yes. Actually, it is not clear in the question that they are talking about px and py orbitals of the same atom, or px of the two atoms, or and py of two atoms. Like, I hope you are understanding what I'm trying to say. Like, yes, px and py are perpendicular to each other, isn't it? See, px and py are perpendicular to each other. So if we consider these two axes of one atom, these two cannot interact to form bonding, because they will be totally perpendicular. So for the according to the question, we will have to consider px of the two atoms and py of the two atoms. Okay. Yes, of course, from the question it is not clear, but to answer the question you will have to consider px orbitals of the two atoms and py orbitals of the two atoms separately. Then only the px and py can interact to give you pi molecular orbitals. Is it clear, Payal? Okay, thank you. And any more question or any comments on the type of questions? Should I include harder questions for the next tutorials, or easier questions, or more descriptive kind of questions should I include? Any comments from your side? Or you can turn on your video also if you want, if you are comfortable. Like, we can have a discussion now. Any comments? Yes, Dr. Payal, from your side, any comment on the kind of question or level of questions? Yes. Sure. I will keep it in mind. Yeah, thank you. Actually, yeah. So what happened? Since it is a week 1 tutorial, and Following the videos uploaded by Professor Neeraja ma'am, I included some easier questions, and I also didn't know the students who are going to join the session. That is why, as week one, I tried to include a few easy level kind of questions. But yes, definitely, like you suggested, I will try to include harder questions from the next sessions. And any more questions or queries? Mr. Arup Sharma, from your side, any comments? Yes? Okay. So, the students are from which, like, from which classes or which courses? Is it BSc level or MSc level or PhD postdoctoral? Can you all please give me a quick introduction? Hello. Okay. So, we will go through the questions discussed today quickly once again. So today we have discussed 15 questions on the topic structure of atoms and molecules and molecular orbital theory. First we calculated the ion isoelectronic with carbon monoxide, which in which we moved forward by calculating the number of electrons present in the species provided in the options, and we were governed by molecular orbital diagrams of the species given in the options. By calculating the number of electrons, we found that cyanide ion is isoelectronic with carbon monoxide. Question number 1 was followed by question number 2, where we had to calculate the energy of these four sets of quantum numbers, where we found out that n plus L, the sum of principal quantum number and azimuthal quantum number, gives us the highest energy possessing quantum number set of these four options. Then we discussed four sets of electronic configurations, which in which one of these four sets violated above principle, and then we quickly revised what above principle dictates, and after recalling the above principle theory, we found out that option B set was violating above principle because the 2px orbital was filled before filling the lower energy level 2s. Then we saw that isotopes of an element have similar chemical but different physical properties. Then we moved to the structure of naphthalene molecule, which contain two fused benzene rings linked by two atoms. This naphthalene molecule was possessing 5 pi bonds. Then we found out the paramagnetic species among cyanide, nitrous, carbon monoxide, and O2 minus. And by looking at the molecular orbital diagrams of these four species, we found out that O2 minus, which contained 17 electrons, was paramagnetic among these four. After that, we moved to the paramagneticity of oxygen molecule, and we asked that the reason could be explained by molecular orbital theory. We found that combination of two atomic orbitals results in the formation of two molecular orbitals. Definitely this question has some conflict. So the query will be cleared in the next session. Before taking the tutorials, I will clear the query in the next session regarding question number 8. In question number 9, we calculated the bond order of oxygen. First, we found how to calculate bond order, and we also discussed how the bond strength or bond length of the molecule in the molecules is dictated by bond order in the molecules. Then we found the percent S character and P character in the hybridization states. Like for example, in this question, we found out that orbitals that are resulted from sp hybridization have 50% S character and 50% P character. We tried to figure out the hybridization, geometry and shape of BCl3 molecule, and we found out that option B was the correct answer. BCl3 molecule was possessing sp2 hybridization and it possesses a trigonal planar shape. In question number 12, we saw these four options and we tried to figure out which of these have planar symmetry. We found out that H2SO4, H2O and CCl4 all were sp3 hybridized, and the geometry or geometries of the shapes of these three molecules were tetrahedral, bent and tetrahedral again. But in case of option C, nitric acid, we had sp2 hybridization and it was containing trigonal planar shape. Yes, yes. Can you repeat? Okay, yes, yes, yes. Geometry of this molecule will be planar, but the shape will be okay. But you will have to see the like how the geometry of the hybridization is dictating the symmetry. If we are talking about okay, okay, I can understand the query. Like for example, in H2SO4 it is possessing tetrahedral and CCl4 also it is tetrahedral, but in water molecule it is placed in the plane. Actually, in the question, I think they're looking at the geometry only, but if we talk about the symmetry, yes, water molecule will also be planar. So I will try to check the answer again. But yes, your query is also correct, and the if we look at the symmetry, water will also be planar only because it is in the plane. So I will check and try to clear your query in the next session before the questions. Is this okay? Hello, is it okay? Okay. Yes, actually, uh, I was also considering the geometry and shape only, but like you pointed out, if we look at the symmetry, it will be water is will also be planar. So I will try to clear your doubt. And then in the question number 13, we found in benzene all the six carbon-carbon bonds have same length, and the reason behind it was sp2 hybridization. We tried to imagine how the unhybridized p orbitals are located in the molecule and how they undergo lateral overlap. And we also talked about the delocalization of 6 pi electrons over this molecular plane. Then in question number 14, we tried to imagine when the main axis of a diatomic molecule is Z and molecular orbital px and py have overlap, like between px orbital of the two atoms and py orbitals of the two atoms. That overlap will give us which of the molecular orbital and we figured out that the option A is the correct answer. Px px and py py will undergo overlap to give us pi molecular orbital. In question number 15, we tried to calculate the formal charge of silicon in silica, and following this formula, we figured out that option A, 0, is the correct answer. Silicon in silica has formal charge 0. So with this, we have discussed 15 questions. Thank you everyone for being with me and for solving the tutorial questions with me.